Alright, so we're going to start this week off with Lab 6. I've kind of printed off the second page here. When you look at Lab 6, the first about 5 pages of it have a bunch of pre-lab questions. So what I want you guys to do is I want you guys to look at the example here of the transformation. It has matrix. So in a previous lab, we talked a little bit about radiography and kind of setting up these different radiographic views. And so this is a matrix that we would find that would give us the transformation of what would happen to the data from here to help get a particular output. So there's some questions I want you guys to kind of look through first, and then maybe come back, and then you'll have maybe a better understanding, or at least having tried them, you'll have played around and think, okay, now how can I do this? So I'm going to skip to the what would normally be the in-class section of this, and so I'm going to kind of write our transformation matrix here. T is 1 1 0 0 0 0 1 1 0 1 0 1 and 1 0 1 0. And so this question says, show that the set of all invisible objects is a subspace of the vector space of all objects. So what we're really trying to look at here is we want to find, there'll be a formal name for this set coming up in this week's lectures, but for now we're just going to kind of play around with it. We want to find essentially the set of all vectors A, B, C, or I should use the x1s. x1, x2, x3, x4, such that our transformation times this vector equals the 0 vector. So why the 0 vector? So it mentions this in the pre-lab. An invisible object is an object whose output is 0. It uses a 0 radiograph. And so we're looking for all possible objects that do this. So if I take our transformation matrix times this vector, and I get an output of zeros, those are the objects I'm looking for. So the way we figure out what this condition is we go ahead and we solve this system of equations. Now remember, when we have the system AX equals B, how we solve is we take A, augment it with B, we find the reduced row echelon form of that, and then we hope to get some identity matrix on the left and what our vector x is over in the augmented form. Now we don't always get the identity. Sometimes we get infinite solutions, sometimes we get no solutions. So this is not maybe the perfect analogy, but most often when we're getting one solution, this is the thing we're looking for. So let's do that. Let's take t augmented with zeros here. So 1 1 0 0 0 0 0 1 1 0 0 1 0 1 0 and 1 0 1 0 0. And what we're going to do is we're going to go ahead and get the reduced row echelon form of this. So reduced row echelon form. And so what we're going to do is we can put this in our calculator or in Octave Online. So if I want my matrix to be a 4 by 5, have entries 1 1 0 0 0 0 0 0 1 1 0 0 1 0 1 0 and 1 0 1 0 0. Okay, so then just verify that this is the matrix we said it was. Great. So now we want to go ahead and get the reduced row echelon form of that matrix. We end up with 1 0 0 negative 1 0 0 1 0 1 0 0 0 1 1 0 and a row of all zeros. Okay, so again, we want to make sure we can, oh, I'm not on the screen anymore. Okay, so we got this is our reduced row echelon form of the matrix. We want to make sure we can then take this and turn this into equations. So the first line right up here says x1 minus x4 equals 0. Second line says x2 minus or plus x4 equals 0. Third line says x3 plus x4 equals 0, and the last line says 0 equals 0, which isn't all that interesting on its own. We do have a free variable because of the no leading 1, which means we have infinitely many solutions, so we can rewrite this to be x1 equals x4, x2 equals x4, and x3 equals x4, and these should be negative x4s, so basically we're subtracting over. So, and we can take this and rewrite the set that we started with, so this will all just work to figure out what this condition was supposed to be. So now we have the set x1, x2, x3, x4, such that x1 equals x4, x2 equals negative x4, and x3 equals negative x4. So really we have the set of all objects x4, negative x4, negative x4, x4, such that x4 is a real number. And so this would describe any possible invisible objects, objects who, when we transform them, put them through the radiographic transformation, end up giving us a 0 output. And so the next question is going to ask us to find a set of objects that spans the set of all invisible objects. And so if we take what we have here, if we want to write this as a span, we can kind of just keep going, right? This is the span of 1, negative 1, negative 1, 1. Okay, so great, we've got a set that spans the set and set it equal to the 0 vector. We have to verify that the only way that this happens is if the coefficients are equal to 0. So if I take this vector and times it by a number to get the 0 vector, the only way that's going to happen is if alpha equals 0. And when we only have one vector, that's going to be the case as long as it's not the 0 vector. So our basis for the space of invisible objects is going to be just 1, negative 1, negative 1, 1. Okay, so that means that if we had anything of the form, I don't know, A, negative A, negative A, what that means is if we take this and we put it through our transformation, we're going to get out an output of 0 from our function. So why is that bad? So say we're looking at a chunk of brain mass here through our transformation, and we find something that just vanishes. It becomes 0. Why is that a problem in radiography? Well, the reason that would be a problem is, say you're trying to go ahead and detect certain things. If you have things that can become 0 or basically fade out or look like something they're not, then maybe there's an issue with part of the brain that we can't detect. Maybe there's some things in there that we don't know about and we're not able to find. And say you have some sort of tumor that forms in that shape, that would be something that would be very bad, because then even though you've done the proper scanning, you've gone to the doctor, went through the radiograph trouble, you still don't actually know what the issue is. Maybe it's disappeared on you. So we want to try to make sure we have something that will not have these invisible objects, because if we do, then we're going to have an issue. So we'll talk a little bit about how linear algebra can help us find these invisible objects in the next coming videos. We also want to talk about the set of all possible radiographs that could be spit out. So what I want to see here is I want to see the set of all t times x1, x2, x3, x4 such that x1, x2, x3, x4 is a possible input for us. We'll say it's from R4 right now. So what we're going to do here is we're looking at this set of outputs. So we're taking 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0 times x1, x2, x3, x4. And our outputs that we're going to get are going to be x1 plus x2, x3 plus x4, x2 plus x4, and x1 plus x3. So we have this potential set of outputs. So this is going to be the set of all x1 plus x2, x3 plus x4, x2 plus x4, and x1 plus x3, such that x1, x2, x3, and x4 are all in the real numbers. So now we've got this set of possible objects we're looking at, and these are going to be the collection of all of the outputs we are going to get from this transformation, from going through this radiographic process. All right, so we want to try to find a basis for this set. So we want to find a linearly independent set of radiographs that spans this space. So continuing on from this idea that we have the set of all x1, x2, x3, x4 in the real numbers, and we've got these outputs, we would normally want to take and write this as the span, and we would go ahead and break down by our components, right? Our x1, our x2, our x3, and our x4. So we would get for x1, 1, 0, 0, 1. For x2, we would get 1, 0, 1, 0. For x3, we'll get 0, 1, 0, 1. And for x4, we will get 0, 1, 1, 0. So now we have a spanning set for this. Great. What that means is that we could go ahead and use these four vectors to describe any possible outputs. But it's not linearly independent yet, is it? Right? So far we just have the spanning set. What we need to show is that it's linearly independent. It'll be much more difficult than for our previous example to do this. So we need to take alpha 1 times 1, 0, 0, 1 plus alpha 2 times 1, 0, 1, 0 plus alpha 3 times 0, 1, 0, 1 plus alpha 4 times 0, 1, 1, 0, and set it equal to the 0 vector. Okay, so let's talk about what equations that'll give us that we need to put into a matrix. Well, it'll tell us that alpha 1 plus alpha 2 equals 0. It'll tell us that alpha 3 plus alpha 4 equals 0. It'll tell us that alpha 2 plus alpha 4 equals 0. And last but not least, it'll tell us that alpha 1 plus alpha 3 equals 0. So then we'll go ahead and put this into a matrix. 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, and 1, 0, 1, 0, 0. Now, if you're looking at this and thinking to yourself, hey, wait a minute, that looks familiar, well, there's a good reason for that. I'm not going to get into that reason for the moment, but take that as you will. So let's go ahead and get the reduced row echelon form, and what do we find? Well, what we find is that we have an infinite number of solutions. So what does that mean for us? Well, what it means is that we don't have a linearly independent set. So here's the thing that we need to then face. How do we create a linearly independent set when we have something that's not linear independent because of free variable? So here's what you do in order to create the linearly independent set that will span the same space. You know how this vector has a free variable? We're just going to make the coefficient 0. That means is that we're only going to use the first 3 vectors for the linear combination. So what does that mean? It means that if we just use the first 3 and we got rid of this one, we would only have one solution, which would be that our coefficients are 0. And what that means is that that first set of 3 vectors is linearly independent. So we won't even use this last one. So our basis for the set of radiographs, here the radiographs are the outputs, remember, is going to then be 1, 0, 0, 1, 1, 0, 1, 0, and 0, 1, 0, 1. Okay, so why do we care about this set, right? So it made sense why we didn't want invisible objects. If we get invisible objects, what happens is we end up with something where we miss things, where things maybe show up looking like other things, and we don't want that. But we want to know what our set of possible outputs is, because if we get something that's not this, what it tells us is that there's an error somewhere in our process. Right, so if we don't get something that is a combination of these 3 vectors as an output, what that means is that either there is something wrong with the way we set up our thing that maybe doesn't match what our assumptions were, maybe our equipment is bad, so that's causing issues, maybe something in our code is bad, but what it tells us is that we don't get something that's a linear combination of these. Somewhere in the process we messed up, because we have to get something that is a combination of these 3 vectors. So then we can go back to the drawing board, we double check our alignments, make sure things are set up the way we think they are, and then we know what sort of things that we have. So these 2 ideas, looking at the set of invisible objects and the set of things that should be our outputs, is going to lead into our discussion for this week. Now, if you're interested in kind of talking about this from a discussion board perspective, you're more than welcome to talk about some of the pre-lab stuff, but in addition, there are a number of questions related to 2 different views. So here's setups B and C. This is in the blank copy as well. Here are their transformation matrices, and there are a number of questions. Basically, you'll be going through the same process that we just did here. You can talk about them, think about whether or not they have certain properties. These ideas of being injective or onto are things that'll make a little bit more sense. Well, I mean, we know the definitions for injective onto, but they might be a little bit clearer once you've gone through this week's notes. And then kind of maybe a bonus fun thing, we want to see if we can come up with something that doesn't have any invisible objects, right? So we talked about how bad it would be to have an invisible object, and we want to know if there's a transformation that we actually could set up to get something that had no invisible objects. So give it a shot. Look forward to seeing what you guys come up with on the discussion boards for this.